Hi, everyone. Today I'm going to talk about lower bounds against the sum of squares algorithm for the problem of independent set on sparse random graphs. My name is Chris, and this is a joint work with a couple co-authors at the University of Chicago, Madhur Tulsiani from TTI, and Jeff Xu from Carnegie Mellon University. Here's the outline of the talk. First, I'll introduce the algorithm and the problem. Then I'll tell you why the existing technique of pseudo-calibration doesn't work, at least not without a fix. I'll tell you some of the analytical techniques we use, and then that will be the end. Okay, so let me start by introducing the algorithm and also the independent set problem, which I'm sure you're familiar with. And yes, this actually is a real emoji. So sum of squares, which I will abbreviate as SOS for the remainder of the talk, is a super strong semi-definite programming, or SDP algorithm. What is a semi-definite program? Well, you can think of it as like a linear program, but with the additional structure that the variables form a matrix, and that matrix is constrained to be PSD, or a positive semi-definite. So SOS is a generic algorithm that can be used to optimize any polynomial subject to polynomial constraints. And the way it optimizes the polynomial is through complete local reasoning and global reasoning through PSD-ness. PSD-ness, which is also called sum of squares reasoning, is what gives the algorithm its name. If you just restrict the algorithm to use complete local reasoning, you get the weaker Shirali-Adams hierarchy. And SOS has seen a lot of successes in recent years. Semi-definite programming in general captures our best algorithms for a lot of important problems, such as max cut and sparse cut. But SOS itself has also been critically important. Thinking about sum of squares reasoning has been important to designing a lot of breakthrough algorithms in several of these areas that I've highlighted in blue. And in all these applications, it's really the PSD-ness, the global PSD-ness constraint that's really important. And this global PSD-ness constraint is also what makes our lives hard for proving lower bounds. So in the remainder of the talk, the main issue that we'll grapple with is this PSD-ness constraint. Okay, so more about sum of squares. The SOS hierarchy is actually a hierarchy of convex relaxations, one for each degree, denoted capital D. And as the degree gets larger, the convex program gets larger, but the value gets better and better as it approaches the true value of the objective function. So we have this chain of inequalities. And the degree is an even integer, which goes from 2 all the way up to 2 times n, where n is the number of variables in the objective function in the polynomial constraints. And here we're trying to estimate alpha g, which is the independent sum of the graph. This can be whatever objective function you want. For our case, it's alpha g. Then the level D SOS program can be expressed as a size n to the d semi-definite program. So what this means is that constant degree SOS corresponds to a polynomial time, polynomial size, semi-definite program, and degree 2n solves the problem exactly, but it requires exponential time. So the main question that we're interested in is how large must the degree be before the value is good, before it approximates the true value of the optimization problem. So let's look at this question, and in particular, we're interested in lower bounds. So to prove a lower bound against, say, polynomial SOS, then we need to prove that the value of the level D SOS hierarchy is significantly larger than the true value for some omega-1 degree, super constant degree. And since SOS is a convex program, the way we can do this is by exhibiting a dual object. And what is the dual object for a sum of squares? It's known as a degree D pseudo-expectation operator, which is denoted by tilde e. So constructing and analyzing pseudo-expectation operators has been really important for both upper bounds and lower bounds for SOS. What we need to do is just build a pseudo-expectation operator. What are some previous techniques for building this pseudo-expectation? So sometimes you can just write down the tilde e exactly and do an exact analysis, and it's great when this works. This paper by Kothari, Mori, O'Donnell, Whitmer introduces a Graham-Schmidt-based technique for analyzing tilde e. The tool of approximate PSD factorization was developed in the context of Planty-Kleek, and this works on random dense inputs. And it's this line of work that our work is closest to, this approximate PSD factorization. And then finally, there's another line of work that is works on lifting the degree 2 sum of square solutions to a higher degree. So our contribution is we work on lower bound techniques for random sparse inputs. And in particular, we extend this approximate PSD factorization technique. So we work on random inputs and they are sparse. So let me clarify exactly what dense and sparse mean. So dense can be, for example, a uniform bit string, a uniformly random bit string over the hypercube of length n, or it could be a Erdos-Renyi graph with constant edge probability, such as 1/2, or it could be a collection of Gaussian random variables. And in general, the input random variables must have moments that are bounded independently of n. In other words, it must be O of 1 sub-Gaussian. On the other hand, the sparse setting, which is what we study, can be GNP for p no longer constant. P is d over n, where d is the average degree of the graph. And now the average degree is no longer linear, it's some sublinear function. And so the moments of the input distribution now depend on n. And the techniques developed in this paper work best for d in the range of polylog n to n. Unfortunately, we're not able to prove results for the constant degree d regime, which is also interesting, but it seems possible that our techniques might be extended to that regime, and that's an area for future work. So let me now give you the statement of our theorem. The independent set problem is denoted by alpha g. It's just what's the largest independent set in the graph. And in a random graph, Erdos-Renyi graph with edge probability d over n, it's known that the largest independent set has size approximately n times log d over d, which is some linear fraction of the vertices. Then the degree 2 SOS relaxation is equal to the Lovász theta number of the graph, is actually significantly larger than the true value. It's a factor of square root d larger than the true value of the independent set. And this was proven by Koja Oklan in 2005. What we prove is that sum of squares also has the same square root d integrality gap with the true value of independent sets. So the formal statement, which is a bit simplified from what's in the paper for the purpose of exposition, it's a bit weaker than what's in the paper, is assuming that the average degree is at least log n, then as long as the SOS degree is subpolynomial, but it can still be super constant, for example, log n is okay, then the value of the SOS degree d program is still approximately square root d times the true value of the independent set. And yes, to prove this, all we need to do is construct a pseudo expectation operator tilde e, which has a large, thinks that G has a large independent set. Okay, so for constructing this pseudo expectation operator, unfortunately, the best heuristic that's worked in the past, pseudo calibration, doesn't work out of the box for us immediately. And let me now tell you why. So to review pseudo calibration, I first need to tell you a bit about Fourier analysis. So recall that if you have a Boolean function defined on the hypercube and going to R, then you can represent it in the Fourier basis, which is just its representation as a multilinear polynomial. And there's one monomial or Fourier character for each subset of the input bits. And this is useful because if f is a function of a random string, the basis is orthonormal. So in independent sets, the input is a random graph, which is represented as a n choose 2 length bit string. And here we can think of -1 if an edge is present and +1 if an edge is not present. So now there is one monomial for each graph on the vertices n, again corresponding to a subset of the input bits. So for example, here is one particular Fourier character for a small graph h that is depicted in this example. Now, functions on the input graph can still be expressed in this basis. For example, here is a function that is 1 if the vertices 1, 2, and 3 form a triangle in the graph and 0 otherwise. So this function just checks whether or not the 3 input bits are all -1. Okay, so pseudo-calibration is defined in terms of the Fourier basis. So I didn't tell you too much about what tilde e, how to construct tilde e, so let me tell you about it now. So we want to construct this tilde E that thinks there is a large independent set. Tilde E is really just a collection of real numbers. So similarly to how in a linear program, the dual solution or primal solution is just specified by a bunch of real numbers, we need to specify those real numbers. And the semantic interpretation of those numbers is they are supposed to be the moments of a fake distribution of independent sets. So there's one real number for each subset of the vertices up to size capital D, the degree. And the moment is supposed to represent the probability that all those vertices are included in an independent set. So for example, pseudo expectation of x1 equals 0.2 means that vertex 1 is included in the independent set with probability 0.2. And the second term, pseudo expectation of x7 times x10 is 0.75, means that both 7 and 10 are in the independent set with probability 0.75. So there isn't a real distribution of independent sets that matches these values, but these real numbers are really just masquerading as a distribution. And they're only moments up to degree D, so you can't get all the moments up to, say, size n. So we need to define these real numbers, and the technique suggested in the context of planted clique is to pseudo-calibrate tilde E using a planted distribution. And what this basically means is we copy the Fourier coefficients of the planted distribution. And here's the exact formula. So if we suppose that D is a planted distribution, say with a G prime and S, then we define the Fourier coefficient of H to just be the matching Fourier coefficient of the planted distribution. And it's just depicted in this formula here. One thing to note is that actually the pseudo-calibrated expression also truncates the size of the Fourier coefficient H to be at most tau. You can see that in the summation. And this is important. It's perhaps the defining characteristic of pseudo-calibration. It means that the pseudo-expectation operator does not take into account high degree information about the graph G. It's only a low degree function of the graph G. Okay, so why doesn't this work for our setting, just defining pseudo-expectation this way? Well, here's the planted distribution for independent sets. First, one should sample a random graph, just T and P, and then one should just plant an independent set by picking each vertex to be in the independent set with probability k over n, and then remove any edges that go between the picked vertices. This is a natural way to plant an independent set of size k in a random graph. So the problem with this is that this distribution is actually distinguishable from GNP with some constant probability. And the distinguisher is super simple. One can just count the number of edges in G. Here, this planting actually disrupts the number of edges in a significant and noticeable way. And in all previous uses of pseudo-calibration, the planted and random distributions are actually hard to distinguish with any constant probability by all polynomial time algorithms, at least conjecturally. So unfortunately, we don't have a planted distribution that we can use for pseudo-calibration for this problem. And you might be wondering, okay, what if you just modify the planted distribution a little bit, fix the edge probability so the number of edges match? Well, if you do that, then you can also just count like the number of triangles and the number of 4 cycles in the graph, and that will distinguish the two distributions. So by counting some small subgraph, you're able to distinguish the planted and random distributions. And we don't know of a planted distribution that cannot be distinguished in this way. So the fix that we use is we use a connected truncation in the definition of the pseudo-calibration. And what this means is we truncate away the global tests in the pseudo-expectation operator. The new definition of the pseudo-expectation operator is that we restrict the Fourier characters to be connected to the vertex set V. So for example, here are some graphs of some Fourier characters that contribute to pseudo-expectation of 1, 2. And the change we make is that we require the Fourier characters to be connected to the red vertex set 1, 2. So we get rid of this one on the right here, which has 2 connected components and 2 vertices which are not connected to the red vertices. So this gets rid of the global checks and the global subgraph counts in the pseudo expectation operator. And once we've done this, now what we must do is prove that this pseudo expectation operator is PSD. Let me now talk a little bit about how we prove that it's PSD through the technique of matrix valued Fourier analysis. And unfortunately, this is not a real emoji. So we need to analyze matrix valued functions of the input graph G. And the matrices have their rows and columns indexed by subsets of the vertices, or subsets of 1 through n. So each entry is a function of G, which means that we can express it in terms of just the Fourier characters on each entry. So we define a ribbon to be a particular Fourier character in a particular matrix entry, and it's specified by the Fourier character and also the index sets. For example, here is a particular ribbon. A represents the set 1, 3, B represents the set 2, 4. Those are the index sets in the matrix. And the Fourier character is telling you which bits of the input to take the parity of. And this particular Fourier character lives in this entry of the matrix. So the ribbons form a basis for the space of all matrix valued functions of the input graph G, just by virtue of the fact that each of the entries of the matrix is spanned by the Fourier characters. So now the next not so obvious step is to group these ribbons together into what we call graph matrices. So a graph matrix, M sub alpha, is the sum of all ribbons with a particular shape, alpha. That is, we collect together the ribbons based on their isomorphism class. Let me explain what this means. Intuitively, one just erases the labels of the ribbon. So this particular shape is the sum of a couple ribbons that live in different entries of the matrix. It's actually the sum over all ways to label the shape alpha. Here's one particular term that appears in the graph matrix. Here's another particular term that appears in the graph matrix. And you can imagine there are lots more. So why would one do this? Well, the motivation is that once you group the ribbons together in this way, actually something incredible happens. It turns out that the norm of the graph matrix is relatively understandable. The norm of the graph matrix has the following formula, which let me put it on the slide. It's a formula that depends on combinatorial properties of the shape alpha, and that gives you the magnitude in n of the graph matrix norm. You can read through this definition, but the important part is that just by looking at this small 5-vertex graph alpha, one can determine the approximate magnitude of the graph matrix M alpha. And it's defined in terms of these vertex separators of the left and right sides of alpha. So because the norm of the graph matrix just depends on alpha, if we want to analyze the spectrum of our random matrix, then now we can do it just by making combinatorial arguments about the small graphs alpha. So let me say a little bit more about how those combinatorial arguments go. The graph matrix basis was actually suggested for planted clique in the dense setting, and there's another norm bound was already proven. We prove a norm bound for the sparse setting, and this has an additional term in it, which is this I highlighted in orange, a term that depends on the number of induced edges in the vertex separator, p to the minus e of s over 2. So in the dense setting, the authors of planted clique use an approximate PSD decomposition to prove that their pseudo expectation operator is PSD, and we are able to use a similar approximate PSD decomposition. And we also are able to use their arguments to handle the vertex factors in our norm bounds. For the edge factors, the ones highlighted in orange, we have to give new charging arguments. And so adopting this charging technique lets us show as PSD, but there's a lot of technical details. I'm not going to go through this slide, but you can feel free to pause the presentation and read it if you're interested. So in conclusion, we develop lower bound technology for sum of squares in the sparse setting, and we do that through a couple ways. First, we amend pseudo-calibration using what we call connected truncation. Second, we prove new norm bounds for sparse graph matrices. And third, we show how to use this technique of approximate PSD factorization and conditioning to do the combinatorial analysis on the shapes. There are some open problems left from this work. Namely, is there a planted distribution, which we could use to pseudo-calibrate? And also, can we extend some of the sum of squares lower bounds to other problems, for example, the regime of constant D, or other problems on sparse random graphs? And thanks for watching.